Alright, so here we are for lesson 2 in unit 5. It says give the vertical and horizontal asymptotes of f of x. And then there's a little reminder under here that says, remember, vertical asymptotes are when, oops, we moved up a little bit here. Vertical asymptotes are when the denominator equals 0 and the numerator does not equal 0. And horizontal asymptotes are given by the limit as x approaches positive or negative infinity. Alright, so we're going to start with the horizontal asymptotes. Alright. So if I take the limit of this function as x approaches, now I'm going to do I'll do positive infinity here, but I'm just going to, we'll write it out here. 2x squared minus 3x minus 2 over x squared plus 2x minus 3. All right. If I take the limit as x approaches infinity, we know that as I approach infinity, that because the degree of the numerator and the denominator are the same, I can just divide out these lead terms here. So I don't have to go through the whole thing of actually plugging in infinity. If I plugged in infinity, I would get infinity over infinity. I could apply L'Hopital's rule. I would have to do that twice. And if I applied the rule twice, we would end up with a limit as x goes to infinity or negative infinity. So maybe I should have put both of them under here and said as x approaches positive or negative. Okay, so that's a rule that, we should know that. We should know that from Algebra 2 and Pre-Calculus, all right? So the vertical asymptote, to find the vertical asymptotes, we need to know when the denominator equals 0. So I'm going to factor out the denominator. I don't care about actually I should check the numerator, because if there's a common factor up top and bottom, let's see if we can even factor the numerator. So we have f of x equals, I know the denominator is going to factor here, so I can see that one. That's x plus 3 times x minus 1. All right, and the numerator here, let's see here, if we can factor it. I think we can here. So I think the numerator is going to factor 2x and x, and this would have to be 2 and 1, and this would be negative and positive. Okay, so the only reason I'm factoring the numerator is to verify that both of these factors give me vertical asymptotes and one of them doesn't give me a hole or something like that in my graph. So I just want to verify that before I say that I have vertical asymptotes at x equals negative 3 and at x equals positive 1 on this graph. Okay? All right. So we're going to be talking about graphs and curve sketching graphs based on information about the graph. And so there's some certain things that we need to know. We talked about these in our last unit, but here we go. If f prime of x is greater than 0 in some interval, then we know that f is increasing in that interval. Okay, so if my derivative is positive, then I know that the function itself is increasing. If the derivative, if f prime is less than 0, we know that f is decreasing. Okay, decreasing on the interval. If f prime is equal to 0, then f is constant. All right, constant on that interval. So that means that it would just be flat with a 0 slope. Okay, and then we want to talk about f prime changes from negative to positive at some value of c. Then we know that f of c is a minimum. All right, now I'm going to draw a picture of what this looks like. Minimum. All right, so we're going to draw a picture of f prime of x changes from negative to positive. So here's f prime of x. So it's coming up here, like something like this, and it changes from negative to positive. And so I'm going to call that f prime of x. All right. Now, anywhere that my derivative is 0, okay, I want to think about this. Anywhere my derivative is 0, that means, let me grab a different color here. That means that my original function f of x has a min or a max there. Now, if you think about this, since my derivative down here is negative, all right, so f prime is less than 0, So that implies that f is decreasing. F prime up here is greater than 0, so that implies that f is increasing. So that means that this point here must be a minimum on the graph of f of x. So that means that f is coming down and decreasing, and then turning and increasing with a minimum right there. So this would be the graph of f of x. Okay, so when we say that f prime changes from negative to positive, we're saying that f is going from decreasing to increasing. All right. Likewise, if f prime changes from positive to negative. So I'm going to actually draw the picture of this one first. So f prime is going from positive, and we'll just say to negative, maybe like that. So here's my point. Okay, again, this is f prime of x. So what that tells me is that because f prime is greater than 0, that means that f is increasing. And down here we have f prime less than 0, which tells me that f is decreasing. So now f is going from increasing to decreasing, so I would have to have some sort of a max. So f might be doing something like this, up and then back down like that with a maximum right here. So if f prime changes from positive to negative at c, then we know that f of c is a maximum. All right? If f prime has an x-intercept at c, but does not change signs at c, okay? So let's draw what that would look like. Let's go back to red here. So if f prime has an x-intercept, so let's say that this is f prime here, and f prime is coming down like this. All right? So you will notice that f prime did not change signs here. Okay, so this is my value of c right here. I guess I should have marked that on each one of these graphs, but on my first graph, this would have been some value of c here. This would have been some value of c here. All right, so if f prime of x has an x-intercept at c, but it does not change, that means that f prime is always positive, which means my graph of f is increasing all the time. There's no place where f is increasing. So that means that f of c is neither a relative max or a min. Okay? There's something else going on with f. So again, my graph of f would have to be always increasing, but because the derivative, this point on f prime, is 0, that means that f would be doing something like this. So we would be coming up like this, maybe a horizontal tangent right there, and then continuing to climb. So we would have a point of change in concavity, but f is still increasing. There's no max or min right there. Okay? All right. Now let's talk about second derivatives. So f has to be differentiable on the open interval if f prime is increasing. So now we're talking about the derivative is increasing on the interval. Then that means that f is concave up on that interval. Okay? So if you think about it, what we're basically saying here is because f prime is increasing, then what we know about that is that f double prime is greater than 0, and if f double prime is greater than 0, then we know we're concave up. Likewise, if f is decreasing on the interval, then the graph of f is concave down on that interval. Okay, and by saying that f prime is decreasing, what we're implying is that f double prime is less than 0, and again, that implies that f is concave down. All right, so that's one way to look at it. Now, I kind of already talked about that in the upper part, but if f double prime is greater than 0, then we know that the graph is concave up. And if f double prime is less than 0, we know the graph is concave down. Points of inflection, the point at which a graph changes concavity. So if f of c is a point of inflection of the graph of f, okay, then either f double prime of c is equal to 0, or f double prime does not exist. Now, what do we mean by that? These are what we called in the previous unit we called these critical numbers. Okay, so critical numbers are numbers where, and we talked about this in terms of first and second derivative, but now we're talking about second derivative. So critical numbers are where f double prime is equal to 0, or f double prime is undefined, or does not exist. Okay, f double prime undefined. All right. Okay, so let's take a look at some curve sketching then. All right. So the first one says, all right, we're given a function x cubed minus 3/2 x squared, and without calculus, what can you tell about the graph? So we're going to look at everything we can possibly say about this graph. Okay, so one of the things I can say is, well, I can find a y-intercept on this graph. I know that this graph has a y-intercept, so if I plug in 0 for x, I'm going to get 0 minus 0, so I guess we get 0. So we know we have a y-intercept at 0, 0. All right. Likewise, we could look for an x-intercept, so we could plug in 0 for y. So we'll do that. We'll do 0 equals x cubed minus 3/2 x squared. So we can go ahead and factor this out. So 0 equals x squared times x minus 3/2. All right. So if I set x squared equal to 0, I get x equals 0. So that tells me I have a 0, 0 x-intercept, which makes sense because I had a y-intercept at 0, 0. And I have an x-intercept at 3/2, comma 0. So I have two x-intercepts on this graph. Okay. Let me see. There's no place that this graph is undefined. This is a polynomial function. Okay. So I know that the right-hand behavior, I know that the right side, okay, so we could say the right side is going to go up. All right. We know that it's going to be doing something like this because the lead coefficient is positive. The left side is going to go down because it's a third degree function, and so third degree functions go opposite directions, so the left side is going to do something like that. The domain of the graph, the domain, all right, the domain of this graph, since there's no restrictions, the domain is going to be x in the set of reals, and the range, because it's a polynomial function and it is continuous, the range would be y in the set of reals. All right, so there's a few things that we know about this graph, and so now we're going to take a look at using some calculus. What can we tell about the graph? All right, so first derivative information. What information about the function do we get from the first derivative? Well, let's take the first derivative. If you take the derivative here, you get 3x squared. And then when you multiply 2 times 3/2, you're going to get 3 times x. So there's my first derivative. So now I want to look at my first derivative, and I want to look at critical values. All right, critical. So again, critical values are where f prime is undefined. So if I look at my function, this is a quadratic function, so there's no place that it's undefined, so I don't have to worry about that. And where is f prime equal to 0? So we'll take this function and we'll set it equal to 0. So we get 0 equals 3x squared minus 3x. If I solve this, I can factor out at 3x, so I get 3x times x minus 1. So that tells me that I have a critical value at x equals 0, and I have a critical value at x equals 1. Okay, so we have two critical values here, and what we want to know is what are those critical values telling us? This is where our derivative is equal to 0. So normally if we were sketching a graph, that means that f has to have maxes or mins at these points. Okay, that's what critical points are, is if the derivative is changing values at x equals 0. So if I'm going from negative to positive or positive to negative, then f of x is going to have a max or a min. So I need to find out if we're actually changing values at x equals 0 and at x equals 1. So the way we're going to do this is we're going to set up a little number line here. So I'm going to draw a little number line under here. Okay. And so f prime of x, so on my number line I'm going to put my critical values in there. So this is going to be 0 and this is going to be 1. And so basically I want to know what's happening. I know that at f prime of 0 is 0, and I know that f prime of 1 is 0. So I know that both of these guys are 0. I want to know what's happening over on the left side of 0. I want to know what's happening between 0 and 1, and I want to know what's happening to the right side of 0. Okay? All I know for sure right now is that somewhere on my graph, okay, if we were graphing f of x, I would have a 0 here, and I would have a 0 here. But I don't know if, if f is increasing here, decreasing here, what's going on. So that's what I'm about to find out. So I'm going to choose a number to the left of 0. So I'm going to choose x equals -1. And I'm going to plug that into my derivative. Okay? So if I plug in x equals -1 to the derivative, that's going to be -1 squared, which is 1, times 3, which is 3. So actually I can do that over here. I'll do f of -1. Alright? So f of -1 is going to be 3. And then -1 times -3 is going to be plus 3. So that's going to equal 6. And that's positive. Okay? So when x is equal to -1, my derivative is positive. Well, why is that important? Because if the derivative is positive, what does that tell me about f of x? That tells me that f of x is increasing. Okay? So now, if I was drawing my graph of f of x, I would know that f of x is increasing as I approach 0. Okay? And actually, I shouldn't do that because it's not this is my derivative graph over here. So I know that f of x is increasing as it approaches 0. And then we're going to plug in a number between 0 and 1. So I'm going to choose 1/2. X equals 1/2. So we'll come over here and we'll do f. This was f prime, by the way. F prime of 1/2. All right. So 1/2 squared is 1/4, and 1/4 times 3 is 3/4. So that's 3/4 minus 3 times 1/2, which is 3/2. Okay. Now, hopefully you can look at that and determine that that's going to be negative. If you actually did the math, you would turn out with -3/4. All right. But I don't care about that. What I care about is that this value over here is negative. So that tells me that my derivative is negative between 0 and 1, which tells me that f is now decreasing. And then I go to the right side of 1, so I'm going to choose x equals 2. And I'm going to find f of 2. And so I plug in, f prime of 2. So I plug in 2 for the derivative, and I get 2 squared is 4. 4 times 3 is 12. And 2 times 3 is -6. So this is positive also, which means my derivative is positive, which means f is now increasing again. Okay? So what does this tell us about the graph? Okay? It tells us that f of x is increasing on the intervals from -∞ to 0 and from 1 to infinity, because f prime of x is positive. Okay? We could also say that f of x is decreasing on the interval from 0 to 1 because f prime of x is negative. All right? Hang on a second. All right. So if we talk about increasing and decreasing, if I know that f of x goes from increasing to the left of 0 to decreasing to the right of 0, that means I have a maximum at 0. So we can now say that we have a max at x equals 0 because f went from increasing to decreasing, and you know what? Actually, I'm going to back up a second. We have a max at x equals 0. You know what? I'm going to back up here. Now, I'm implying something that we already said above, but if I'm going to say that we have a max, how do I know that there was a max? I know that there was a max because f prime went from positive to negative. Okay? I have a max at 0 because f prime went from positive to negative, positive to negative, and that is what implies that f went from increasing to decreasing. Okay? So again, I'm using the information that I was given. I knew about f prime of x. I knew that f prime went from positive to negative. Therefore, f went from increasing to decreasing. So I know that there's a max at 0. I also know that there's a min at x equals 1 because f prime went from negative to positive, and you can see that in our number line. So at 1 we were negative to the left of 1, positive to the right of 1. So negative to positive, which implies that f went from decreasing to increasing. Alright? And if I actually wanted to know where those maxes and mins were, I could take my original function and I could plug in 0 to the original function. So if I go back to f of x and I find f of 0, I find out this is, now again, I can't see the function, but you've got the function at the top of your paper there. It's x cubed, so that would be 0 cubed minus 3 halves times 0 squared, which is going to equal 0. So I know that I have a max at the point 0, 0. And I know that there's a min, so I'm going to plug in f of 1. So that's going to give me 1 cubed minus 3 times, or 3 halves, times 1 squared. And that's 1 take away 3 halves, which is negative 1 half. So I have a min at 1 comma negative 1 half. Alright? Alright. Let's take a look at the second derivative now. Alright? What is the second derivative going to tell us? So our first derivative was 3x squared minus 3x. If I take the second derivative, that's going to be 6x minus 3. And now we're going to look at the critical numbers. Alright, so we look at the critical values again. So we're going to look at where f double prime is undefined. So if you look at this function, this is just a linear function, so that's not undefined anywhere. Alright, so we don't have to worry about that. And we're going to look at where f double prime is equal to 0. So if I set f double prime equal to 0, I get 6x minus 3. If I solve this, I'm going to add 3 and divide by 6. I get x equals 3 over 6, which is 1 half. Alright, so I have a critical value at a half. Alright? Now, if I can show that f double prime goes from negative to positive or positive to negative, then I can show that this is a point of concavity. Alright? So we're going to do the same thing that we did with f prime. We're going to draw a little number line here. Okay? So we're going to take and we're going to look at f double prime this time. And I'm going to look at the value of 1 half. And I'm going to see what's happening with f double prime of x. And then we're going to say what's happening with f of x. Alright? So f double prime of x, if I start at 1 half and I go to the left, I could do x equals 0 to the left. Alright? So again, I'm going to plug in 0. Now you can see up here at the top, if I plug in 0, this is going to be negative 3. So that tells me that f double prime is negative at x equals 0. So I come over to the other side and I plug in x equals 1. And so 6 times 1 is 6 minus 3. This is going to be positive. Well, if f double prime is negative, that means f is concave down. If f double prime is positive, that means f is concave up, which means that x equals 1/2. Okay, so now we have what all this implies is that x equals 1/2 is a point of inflection because f double prime changed from negative to positive at x equals 1/2. Okay, so that's how we know that that's a point of inflection, is we have to change from negative to positive. All right, so we have all this information floating around on these 2 pages, and now we're going to put all this information together and take a look and see what it's telling us here. Okay, so we're going to organize our data on the number lines below. So I've got 2 number lines this time, and I'm going to put 0 over here on the first number line, and my 1 over here, and then down on the other number line, that means that 1/2 would be right in the middle here. And I'm going to organize all that data from the 2 number lines that I had. So my first number line, we were talking about f prime of x, all right, and we made some inferences about f of x. And then the second number line, we were talking about the second derivative, f double prime, and we made some inferences about f of x based on that as well. All right. So on your first number line, we said that f prime was negative over here, positive between 0 and 1, and negative from 1 to infinity. On our graph of f double prime, we said that f double prime was negative from negative infinity to 1/2, and positive from 1/2 to infinity. All right? And so what we're trying to do is get all the information about f of x. So f of x, we would say, is, did I write these wrong here? Positive, I wrote these backwards up here. Sorry about that. Let me go back and check my first number line here just to make sure. Okay, I just want to double check here and make sure I wrote those correctly. Positive, negative, positive. Yep. All right. So f prime was positive, then it was negative, then it was positive. All right. So what that told us was that f was increasing, f was decreasing, and that f was increasing. And then we said that f was concave down, and then concave up. All right. Now we also had some other information from the first page. We know that the y-intercept of f was at 0, 0. We know we had an x-intercept at, gotta go back and look at my first page again here. We had an x-intercept at 3/2, it looks like. So we had an x-intercept at 3/2, comma 0. Okay. And I didn't mention it at the time, but I should probably mention it now. We had, when I look at my, let me go back to, notice my x squared here. My x squared, when I set it equal to 0, that represents a double root of 0, which implies that this x-intercept is going to be a bounce on the graph of f of x. All right, so that might be helpful to know that as well. So at 0, 0, which is our y-intercept and one of our x-intercepts, I believe we should have a bounce right there. Okay? All right. What else did we have from the first page? We knew that the right side was up. Okay? So we knew that the right was up. We knew that the left was down. So we know that's happening. We already talked about the domain and range. We should see that in just a minute. And now we're going to attempt to put all of this information on this graph right here. Okay? Let me see. Oh, we also had a min in there as well. So we had a max at 0, 0. Okay, that's going to be our bounce. We also had a min that we found at 1, negative 1/2. All right, so that's a point on our graph as well. All right, so I'm going to zoom out a little bit here so that we can see a little bit more of this. So we'll zoom out a little bit. All right, there we go. That looks better. All right, so I'm going to start by graphing the points that I know are here. So I know I've got a 0, 0. I know I have the point 3/2, 0, so that's over here. I know I have a minimum at 1, negative 1/2. So I have a minimum right here. All right, and now I'm going to go back to my number lines, and I'm going to look at the areas where f is increasing. Now, if you look, f is increasing from negative infinity. I'll do some highlighting here. So I know that f is increasing from negative infinity to 0, and then I'm increasing from 1 to infinity. At the same time, I'm going to be concave down from negative infinity all the way to 1/2. Now, that means that from negative infinity to 0, I'm increasing and concave down. So there's increasing and concave down. Okay. Now, we have a bounce at 0, 0, but we also know that that 0, 0 was a max. So that was actually with my min on the previous page as well. So that is a max, which makes sense because my graph is supposed to stay concave down all the way until I get to, whoops, a little bit high right there, that's okay. My graph is supposed to stay concave down until I get to 1/2. Oops, I didn't do 1/2. Did I graph the wrong point here? My min's at 1, negative 1/2. Where is my point of concavity? Is at negative 1/2. Okay, so I'm supposed to be concave down until I get to 1/2. All right, so I actually need to plug in 1/2 to find my point of inflection. So if we plug in 1/2 to f of x, all right, so again, going back to f of x, this would be f of 1/2, and f of 1/2 is going to be 1/2 to the third power minus 3/2 times 1/2 to the second power. That's going to be 1/8 minus 1/2 squared is 1/4. 1/4 times 3/2 is 3/8. So that's going to end up being negative 2/8 or negative 1/4. So I actually have a point of inflection at 1/2, negative 1/4, which is somewhere right about here. So I'm curving down until that point, and then I turn concave up, and I'm still decreasing. So as I turn from concave down to concave up, I'm still decreasing. I'm still concave up, all right? And I'm concave up from 1/2 to infinity. And there's the graph of f of x. All right? And that's it for this lesson. All right, we'll do another one tomorrow.